All right, so welcome back. So let's look at this example. We want to construct the group tables for Z2 cross Z3 and Z6 and compare them. Now, notice that Z2 is a group under addition and Z3 is also a group under addition. Z6 is a group under addition as well. So the operation of this external direct product is going to be component wise, and it will be in the first coordinate the operation would be addition mod 2. In the second coordinate the operation would be addition mod 3. Okay, so here are the group tables for these two groups. So Z6 you are already familiar with. I'm pretty sure you have created the group table of Z6 in one of your homework. So you get this 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5 here, and then for example, if we add 2 and 4 here, we get 0 because 2 plus 4 is 6, modulo 6, that's 0, so 2 plus 4 is 0. And 3 plus 5 is 7. 3 plus 5 is 8. 8 mod 6 is 2. So this is the group table for Z6. Here I have, so Z2 cross Z3 has 6 elements. So there are 2 elements here and there are 3 elements here. So there would be 2 times 3, 6 elements in this group. Here are the 6 elements here. So 0, 0, 1, 1, 0, 2, 1, 0, 0, 1, and 1, 2. These are the 6 elements of this external direct product. So, and this is where we created the group table. So let's, as an example, let's look at 1, 2 added with 1, 2 here. So if I add 1, 2 and 1, 2, so we're going to be adding the first, we will be adding, so we are adding 1, 2 and 1, 2 here. So if we add the first coordinates, we get 1 plus 1 is 2 and 2 mod 2 is 0. And in the second coordinate, we are adding 2 and 2, which is 4. 4 mod 3 is 1, so you're getting 0, 1. Let's do another one. So let's say 0, 2 added with 1, 0. So 0, 2 added with 1, 0. So 0 plus 1 is 1. 2 plus 0 is 2. So we get 1, 2 right here. So 0, 2 plus 1, 0 is 1, 2 here. Okay, so you should check that these two tables are correct. And so looking at these two tables, notice that both of these groups have 6 elements. And notice that Z6 is a cyclic group and it is generated by the element 1. The question is are they pretty much the same groups here? Well, here's what I'm going to do. I am going to map both of these groups into a third set in the following way. So I'm going to map 0 to A0, 1 to A1, I'm going to map 2 to A2, I'm going to map 3 to A3, 4 to, we're going to map 4 to A4 and 5 to A5. Similarly, we're going to map 0, 0 to A0. We're going to map 1, 1 to A1. We're going to map this one to A2, A3, A4, A5. So let's do that. So we are setting A0 equal to 0, A1 equal to 1, A2 equal to 2, A5 equal to 5 in the group Z6. And in the external direct product here, we are setting A0 to 0, 0, A1 to 1, 1, A2 to 0, 2, and so on. So if we make this, so we are mapping these elements of these two groups to the set of 6 elements A0 to A5. And if we make this substitutions in the table, in the two tables here, what we get is this. And you can notice that these two tables are identical. So what it means is that these two groups are isomorphic, which we haven't defined yet, but we will be defining soon. But roughly speaking, it means that as groups, they are the same. So in terms of group properties, they are identical. Now, you might not have realized that that Z6 is cyclic generated by 1, and in fact the reason I wrote the elements of Z2 cross Z3 in the order of 0, 0, 1, 1, 0, 2, 1, 0, 0, 1, 1, 2. So notice that I wrote the elements of Z2 cross Z3 in a specific order here, and the reason I did that is because 1, 1 is a generator of this group. So if I add 1, 1 twice, I'm going to get 0, 2. If I add 1, 1 3 times, I'm going to get 1, 0. If I add 1, 1 4 times, I'm going to get 0, 1. If I add 1, 1 5 times, I'm going to get 1, 2. So 1, 1 is a generator for this group, and 1 is the generator for this group. So both of them are actually cyclic, and they both have order 6, so they must be identical. All right, here is the Klein 4 group. It is the direct product of Z2 and Z2. So Z2 and Z2, so there are 4 elements here. So 0, 0, 1, 0, 0, 1, 1, 1. And here is the group table for this group. So this is known as the Klein 4 group. One thing I would like you to realize is that notice that the order of each of these elements is 2, except for the identity element here. So if you look at 1, 0 and 1, 0, if you add 1, 0 and 1, 0, right? So if you add 1, 0 twice, you're getting the identity. So that means the order of 1, 0 is 2. Similarly, the order of 1, 1 is also 2, because 1, 1 added with 1, 1 is the identity. So every non-identity element here has order 0. Sorry, it has order 2. So in the Klein 4 group, I'm going to make the following substitutions. So 0, 0 will be substituted with E, 1, 0 with A, 0, 1 with B, and 1, 1 with C. So we made those substitutions, and then we are writing the table in terms of A, B, and C. And E. No, you can see again that 2A is identity, 2B is also the identity, and 2C is also the identity. So every element other than E has order 2. Also notice that A plus B, so if we add A and B, we get C. If we add A and C, we get B, and if we add B and C, we get A. In other words, if you look at the non-identity elements A, B, and C, if we add any 2 of them, we get the third one. Recall that by Lagrange's theorem, the order of an element divides the order of the group. Now the Klein 4 group has order 4, so the order of an element could be either 1, 2, or 4. And if we had an element of order 4, then this will become cyclic. But we don't have an element of order 4 here. Every element has order 2, and only the identity element has order 1. So we don't have an element of order 4 in this group. If we had one, then this would be a cyclic group. So anytime we find a group of order 4, and then we see that every non-identity element has order 2, then we know that that group is identical to the Klein 4 group. Okay, so now let's look at the group table, or the multiplication table for S3. This is the group of permutations on 3 elements, and there are 6 permutations here, and they are listed out in here. So this is the identity permutation. This is the cycle. This is a cycle of length 3. This is a cycle of length 3, and then these are cycles of length 2, or transpositions. So these are the 6 elements of S3, and here is the table. Let's check one of them. So if I multiply 1, 3, and 2 with 1, 2 here, then I get 2, 3. Why? Because 1, 2, so 1 goes to 2 and 2 goes to 1, so we know that 1 goes to 1, so that's why we are not writing here 1 goes to 1. Now 2 goes to 1 and 1 goes to 3, so we know that 2 goes to 3, and then 3 goes to 3 here, and then 3 goes to 2 here, so we know that 3 goes to 2. So you can check that if you multiply this and this, you're going to end up with 2, 3. Once again, we're going to make some substitutions here. So we are going to substitute the identity permutation here by E. We're going to substitute 1, 3, and 2. Sorry, we're going to substitute 1, 2, 3 by A. We're going to substitute 1, 2 by B. So 1, 2 is replaced with B. 1, 2, 3 is replaced with A. Then we know that the order of A would be 3 because this is the length of this cycle is 3. The order of a cycle is the same as the length, so the order of A is 3. Order of B is 2. That is, A cubed is the identity and B squared is the identity. And you can also check directly that B times A is the same as A squared B. So if I reverse the order, if I try to reverse the order of A and B, then I'm going to have to write A squared B. I cannot write AB. So BA is equal to A squared B. Now, these 3 equations determines the entire group table. That is, we can express every element of the S3 as a product of the form a to the I times b to the j, where I could be 0, 1, or 2, and j could be 0 or 1. So for example, a squared is 132, a cubed is the identity, b squared is the identity, ab is 113, a squared b is 23. So anytime we have a group of order 6 where we have an element of order 3 and we have an element of order 2, and they satisfy this equation here, then that's going to be identical to S3. So after we make these substitutions in terms of A and B, here's how the group table looks like. So notice that every element of S3 can be written as a product of the form a to the I and times b to the j. And so you should look more closely into these tables and make sure that this sinks in. All right, so I'm going to stop here, and in the next video we will be looking at the orders of elements of external direct products.